Hello and welcome back to Math Zone African Motives. Today, we're diving into a powerful differentiation technique called logarithmic differentiation. Our main goal in this video is to teach you how to differentiate complicated functions by using logarithms. By the end of this tutorial, you'll be able to apply a three-step method to tackle functions that are difficult to differentiate using standard rules like the product, quotient, or chain rule. Let's first understand why we need this method. You're likely familiar with basic differentiation formulas. For a power function, y equals x to the power of n, the derivative dx is n times x to the power of n minus 1. For an exponential function, y equals a to the power of x, the derivative is a to the x times the natural log of a. And the derivative of the natural exponential function, y equals e to the x, is simply e to the x. But what happens if both the base and the exponent are variables? For a function like y equals x to the x, the derivative isn't immediately obvious. This is where logarithmic differentiation becomes not just useful, but necessary. Logarithmic differentiation allows us to turn complicated structures like products, quotients, or functions with variable exponents into simpler forms using the laws of logarithms before we differentiate. This process makes the differentiation much easier. So, to become a master of this technique, we first need to review those essential logarithmic laws. Let's do that next. Welcome back. In this section, we'll quickly review the logarithmic laws that are the foundation of logarithmic differentiation. Without a strong grasp of these, the method won't work. First up is the product rule. The natural logarithm of a product x times y is equal to the sum of their individual logarithms. So, multiplication inside the logarithm becomes addition outside. This is incredibly useful for splitting up complex products. Next is the quotient rule. The natural logarithm of a quotient x divided by y is equal to the natural logarithm of the numerator minus the natural logarithm of the denominator. Division inside the logarithm becomes subtraction outside. This is our key tool for simplifying fractions within a logarithm. And finally, the power rule. The natural logarithm of x raised to the power of m is equal to m times the natural logarithm of x. This rule is the most important for our method. It allows us to take an exponent, which is often a function, and bring it down as a coefficient. This changes a variable in the exponent into a product of functions, which we know how to differentiate with the product rule. Let's quickly cover some special cases. The natural logarithm of 1 is always 0, and the natural logarithm of e is always 1. These basic laws will be crucial in every example we solve. Make sure you're comfortable with them. Now let's look at the correct application of these rules. Before we apply these laws, it's vital to know where not to apply them. Let's look at some common mistakes to avoid. First, the logarithmic laws we just saw are for products and quotients, not for sums or differences. A very common error is this. It is incorrect to say that the natural log of x plus y equals the natural log of x plus the natural log of y. The same applies to subtraction. Remember, these laws only work for multiplication and division. Second, be careful with the power rule. The exponent only applies to what it's attached to. For example, it's wrong to say the natural log of x times y to the m is m times the log of x times y. The exponent m is only on y. So first we'd use the product rule to get ln x plus ln y to the m, and then the power rule to bring the m down, resulting in ln x plus ln y. Now let's establish the general procedure for applying this method to any function. This is the heart of what we're learning today. There are three core steps to logarithmic differentiation. First, take the natural logarithm of both sides of your equation. Second, simplify the expression using the logarithmic laws we just reviewed. Third, differentiate both sides of the equation with respect to x, remembering to use implicit differentiation on the y side, and then solve for di dx. Step 3, differentiation, requires a special tip that connects the chain rule to this method. If you are differentiating y with respect to x, You differentiate y as normal and then multiply the result by di dx. This is implicit differentiation. Specifically, the derivative of the natural log of y is 1 over y times di slash dx. Remember this, it's a key part of every problem. With these rules and tips in mind, we are now ready to tackle our first example. Let's make this theory come alive. All right, let's work through our first example. This will demonstrate the three-step method in action. The problem is to determine dx dx if y equals the cube root of the quantity x squared minus 1 divided by x squared plus 1. Notice how complex this function is. It's a quotient and a cube root. Differentiating it directly using the quotient rule and chain rule would be very messy. But with logarithms, we can simplify it beautifully. Step 1. Take the natural logarithm of both sides. This is always our first move. So we get the natural log of y equals the natural log of the cube root of our original function. Step 2. Simplify using the logarithmic laws. First, let's rewrite the cube root as an exponent. The cube root is the same as raising to the power of 130. Now we can apply the power rule to bring this exponent to the front as a coefficient. Next, inside the logarithm, we have a quotient. Let's apply the quotient rule. The logarithm of the quotient becomes the difference of the logarithms of the numerator and the denominator. Look at how much simpler this expression is now. We have transformed a cube root of a quotient into simple addition and subtraction of logs. Step 3. Differentiate both sides with respect to x. We'll start with the left side. The derivative of ln y is 1 over y times di soc y. That's our implicit differentiation. Now for the right side. We differentiate each term inside the brackets. The derivative of ln x21 is 1 over x21 times the derivative of the inside, which is 2x. Similarly, the derivative of ln x1 is 1 over x21 times its inside derivative, also 2x. Notice the minus sign from the quotient rule. Now let's put it all together. We have the left side equal to the right side. This gives us 1 over y times di dx equals 1/3 of the difference of those two terms. We are almost there. Our goal is to find di r dx. We just need to isolate it. Let's start by multiplying both sides by y. So dl dx equals y times that entire expression in the brackets. But our final answer shouldn't have y in it. We must substitute back the original expression for y. Let's also factor out the common 2x from the bracket. Substituting I and factoring gives us this line. Now we can simplify the expression inside the bracket by finding a common denominator. The common denominator is the product of the two terms. The expression simplifies to x squared plus 1 minus the quantity x squared minus 1, which equals 2. Let's plug this simplified form back into our equation for di slash dx. We now have di r dx equals 1/3 times 2x times y times 2 divided by the product of x squared minus 1 and x squared plus 1. This is a valid answer, but we can clean it up by combining terms. Let's substitute y's exponent form, x21 plus 1 to the 1/3 power. Notice we have a term, x21 to the 1/3 in the numerator, and x21 to the power of 1 in the denominator. We also have x1 to the 1/3 in the numerator and x1 to the power of 1 in the denominator. Using exponent rules, a to the m divided by a to the n is a to the m minus n. Performing the subtraction in the exponents gives us our simplified final answer. Di slash dx equals 4x divided by 3 times the quantity x squared minus 1 to the power of negative 2/3 times the quantity x squared plus 1 to the power of negative 4/3. Let's compare this with the memo. The memo's answer is di slash dx equals 4x divided by the quantity 3 times x21 to the 2�3 power times x2 plus 1 to the 4�3 power. Our answer matches perfectly. Verified using memo. We have successfully differentiated this complex function using logarithmic differentiation. Let's move on to our second example. This problem highlights a critical aspect of logarithmic differentiation. You cannot use it on a sum of terms. The question is to find di dx if y equals x to the power of sine x plus sine x to the power of x. Our objective here is to learn how to differentiate a function that is a sum of two other functions with variable exponents. At first glance, it might seem natural to take the natural log of both sides immediately. But if we did, we would have ln of a sum. And as we saw earlier, there is no logarithmic law to simplify ln of a plus b. You cannot split a logarithm over addition. Because this is a sum, we must split the problem. We'll differentiate each term separately and then add the results. The sum rule for derivatives, di dx equals du dx plus dv, allows us to do this. We'll let the first term be u and the second term be v. So we have y equals u plus v, where u is x to the sine x, and v is sine x to the x. We will now find du dx and dvx independently. This gives us a strategy. First, find the derivative of u. Second, find the derivative of v. And third, add those derivatives together. Let's begin with the first term. U equals x to the sine x. This is a classic case for logarithmic differentiation because it has a variable exponent. Following our three-step process, we take the log of both sides. This gives ln of u equals ln of x to the sine x. Now we use the power rule to bring the exponent down. We get ln of u equals sine x times the natural log of x. Now for step 3, differentiate both sides with respect to x. On the left, the derivative of ln u is 1 over u times du dx. On the right, we have a product of two functions, sin x and ln x. So we must use the product rule for differentiation. The product rule says the derivative of the first function times the second, plus the first function times the derivative of the second. The derivative of sine x is cosine x, and the derivative of ln x is 1 over x. Applying the product rule, the right side becomes cosine x times ln x plus sine x times 1 over x. Now we solve for du dx by multiplying both sides by u. Du dx equals u times the quantity cosine x times ln x plus sine x over x. Finally, we substitute back our original expression for u, which is x to the sine x. This gives us our result for the first part. So du dx is x to the sine x times the bracketed expression. We'll save this result and now proceed to find dv dx. Welcome back to the second part of our example. We have found d equal to dx, and now we need to find dv dx for the second term, v equals sine x to the x. This again is a function with a variable exponent, so we'll use the same three-step process. Step 1. Take the natural logarithm of both sides. We get ln of v equals ln of sine x to the x. Step 2. Simplify using the logarithmic laws. Using the power rule, we bring the exponent x down to become a coefficient. So ln v equals x times ln of sine x. Step 3. Differentiate both sides with respect to x. On the left, we use implicit differentiation to get 1 over v times dv d. On the right, we again have a product, x times ln of sine x, so we'll use the product rule. Here, f is x and g is ln of sine. The derivative of x is 1. The derivative of ln of sine x requires the chain rule. It's 1 over sine x times the derivative of sine x, which is cosine x. Applying the product rule, the derivative of the right side is 1 times ln of sine plus x times cosine x over sine x. We can simplify cosine over sine to cotangent x. Now we solve for dv dx by multiplying both sides by v. So dv dx equals v times the quantity ln of sine x plus x cotangent x. And finally, substitute back the original expression for v, which is sine x to the x. This gives us our result for the second part. We are now ready for the final step. Welcome to the final scene of our tutorial. We've done the hard work of finding du dx and dv dx. Now let's put it all together to find our final answer for dx. Remember, our strategy was to differentiate u and v separately and then add their derivatives. We derived that dx equals the derivative of u plus the derivative of v. Let's recall what we found for each term. This was the expression we found for du dx, the derivative of the first term. And this was the expression for dv dx, the derivative of the second term. The final step is simply to add these two results together. So, our final answer for dx is this entire sum. We have the derivative of the first term, x to the sine x times its bracket, plus the derivative of the second term, sine x to the x times its bracket. Let's quickly check our answer against the memo to ensure accuracy. The memo shows the same exact sum. We have the x to the sine x term and the sine x to the x term both inside their correct brackets. The answers match perfectly, verified using memo. We have successfully differentiated a function involving a sum of terms with variable exponents by breaking it down into separate manageable problems. Let's quickly recap what we've learned today. We've learned about logarithmic differentiation, a powerful three-step method to differentiate complex functions, especially those with variable exponents. We reviewed the crucial logarithmic laws, and most importantly, we learned that this method only works on single terms or products quotients, not on sums or differences. Thank you for watching this tutorial from Math Zone African Motives. I hope this explanation has been clear and helpful. If you found it useful, please give it a thumbs up and leave a comment below. And of course, subscribe for more tutorials from Math Zone African Motives. See you next time.